In this video, let us try to understand how to write the Verilog code of 4-bit binary adder and subtractor. This is a block diagram of 4-bit binary adder and subtractor. So 4 bits are present. So I am making use of 4 full adders, FA0, FA1, FA2 and FA3. And here within the same hardware I want to perform both addition as well as subtraction. For this sake, I am making use of this signal called as mode signal. As single variable is present, I can give 0 or 1. If I give 0, it should perform addition. If I give 1, it should perform subtraction. For the sake of switching, I am making use of these XOR gates. And inputs are A, B followed by Cin. Outputs are sum 0, sum 1, sum 2 and sum 3. Cout is the final carry output. Cin is the initial carry input. And here as it is 4-bit, that's the reason here it is B3, B2, B1, B0. Similarly in A also A3, A2, A1 and A0. Here C0, C1 and C2 indicates the internal carry and C output is the final carry. Let us see the theoretical part now. A 4-bit binary adder and subtractor is a digital circuit that can perform both addition and subtraction of two 4-bit binary numbers. Just now we have seen this point. To implement a 4-bit binary adder and subtractor, we can use a combination of 4-bit triple carry adder and a 4-bit triple carry subtractor. Already we have made a video on 4-bit triple carry adder. Kindly check out the playlist of DSDV lab. Next, the 4-bit triple carry adder takes two 4-bit binary numbers as inputs and produces a 4-bit binary sum as output. Whereas if it is 4-bit triple carry subtraction, then we get output, that is difference. To perform the addition or subtraction using the same circuit, we can use XOR gate. So here I am making use of this particular XOR gate for the sake of switching between two modes of operation, that is addition and subtraction. If XOR input, if it is 0, it should perform addition. If XOR input, if it is 1, it should perform subtraction. Just now I have shown, that is mode signal. If m is equal to 0, it should perform addition. If m is equal to 1, it should perform subtraction. You can call it either mode or else you can call it as Cin. If Cin is 0, it will perform addition. If Cin is equal to 1, it should perform subtraction. Next, in this circuit, A3 to A0 and B3 to B0 are the two 4-bit binary numbers to be added or subtracted. S3 to S0 are the 4-bit binary outputs of adder or the subtractor. So suppose we know that if addition is to be performed, we get output as sum. If it is subtraction, we get output as difference. Let us see the two modes of operation. For addition mode, the 4-bit binary number A3 to A0, B3 to B0 are added using the 4-bit ripple carry adder to produce 4-bit binary sum, that is sum 3 to sum 0, meaning S3, S2, S1 and S0. The XOR input is set to 0 for the sake of addition operation. Next, for subtraction operation, the 4-bit binary numbers A3 to A0 and B3 to B0 are subtracted using 4-bit ripple carry subtractor to produce a 4-bit binary difference, that is S3 to S0. I am making use of the same variable here. Here XOR input should be set to 1 to select the subtraction mode and the circuit performs subtraction. Here you need to remember this note here. When performing subtraction, we need to use 2's complement representation of second input number B to obtain its negative value, which is added to the first input A to perform subtraction. See here, for the sake of addition, we know that it is A plus B. If it is subtraction, it should be A minus B. But I want to perform addition and subtraction within the same hardware. So I'll write this A minus B as A plus of minus B. So that's the reason this minus B should be written as 2's complement number. This is the only change. Now let us try to understand the same thing by taking an example. Here I am taking C input as 0. So let me check whether it is performing addition or not. So I'll take A, which is 4-bit size. So A is equal to 4 ones. Similarly, B is equal to 4 ones. I am performing A plus B operation. So see here, 1 plus 1, 1 plus 1 is carry 1 sum 0, 1 plus 1 plus 1 is carry 1 sum 1. Again same, 1 plus 1 plus 1 is carry 1 sum 1. Here also carry 1 sum 1. This is sum, this is C out. So C out should be 1. Okay, we got C out as 1. This is sum 3, this is sum 2, this is sum 1, this is sum 0. So it is 1 1 1 0, which is for C input is equal to 0. So it is performing addition operation. Now let me analyze it by applying the same to this particular block diagram. C input is equal to 0 means all these points will be 0, and this is XOR gate. For XOR gate, when inputs are same, output will be 0 or else it should be 1. So here all these will be 1s, and full adder which is containing 3 inputs, that is 1, 1 and 0. So 1 plus 1 plus 0 is carry 1 sum 0. So I am getting this as 1 and this is 0. Similarly 1, 1 and 1. So carry 1 and sum 1. Same thing again, 1 plus 1 plus 1 is carry 1 sum 1. Similarly 1 plus 1 plus 1 is again carry 1 sum 1. So let me check whether I am getting this answer or not. So I got C output is equal to 1 and it is 1110. The same thing I got. So this particular block diagram is functioning as an adder if I take C input is equal to 0. Now let us see the operation if I take C input is equal to 1. Here I am performing subtraction, which is nothing but A minus B. As I told you earlier, within a single hardware I have to perform both addition as well as subtraction. So I can write this A minus B as A plus of minus B. So this should be 2's complement. So I am taking the value of A as 1 1 1 1 and B is 1 1 1 1, and I have to take 2's complement of it. So 2's complement is nothing but 1's complement plus 1. So first take the 1's complement of B. 1's complement is nothing but changing 1 to 0 and 0 to 1. So here all 1's are there, so it will be all 0's plus 1, so that I will get 2's complement. So simply add 1 so that this becomes 0 0 0 1. Now this will be the equivalent for minus B. So A plus of minus B. A is nothing but 4 1's, whereas the answer for this is 0 0 0 1. Now try to perform the addition of these and check the result. So I am taking 4 1's here followed by 0 0 0 1. Try to add them. So 1 plus 1 is carry 1 sum 0. Again 1 plus 1 is carry 1 sum 0. 1 plus 1 is carry 1 sum 0. 1 plus 1 is carry 1 sum 0. So this is answer for sum. This is the answer for C out. So let us cross check the answer. I got C output as 1, the same thing which is shown here, and all are zeros. So here I am getting all zeros. Now we shall apply the same thing to this particular hardware. So I am taking C input is equal to 1. So all these points will be 1. This is nothing but an XOR gate. If inputs are same, output will be 0 or else it will be 1. So C input is equal to 1. So let me write 1's here. And this is XOR gate. When inputs are same, output will be 0. Now let us try to perform the addition operation. 1 plus 0 plus 1, which is carry 1 sum 0. Next 1 plus 0 plus 1, again carry 1 sum 0. Next 1 plus 0 plus 1. So I am getting carry 1 sum 0. Again 1 plus 0 plus 1. I am getting carry 1 sum 0. So I am getting 4 zeros here, 1, 2, 3 and 4. The same thing which we got here, and now C output is equal to 1. C output is equal to 1. So this hardware is functioning as an subtractor. Now let us see how to write the Verilog code for it. So in the earlier diagrams which we have seen, it contains 4 full adders. So our step 1 will be writing Verilog code for full adder. This is the logic diagram of full adder. I have explained the functionality of full adder followed by writing the Verilog code of it in my previous videos. Kindly check out the playlist by the name DSDV lab. So it starts with module name and port list. So here output is nothing but sum. So sum is one of the output, and another output is carry. Input is A, another input is B, another input is C in. Next, let me check how many wires are there. So wire 1, wire 2 and wire 3. So wire 1, wire 2 and wire 3. So these intermediate lines which are not having any name should be indicated with some variable. I am indicating them with W1, W2 and W3. Next, let us write for gates. So first gate is XOR gate, XOR X1. For this gate I am writing XOR X1. Output is wire 1, output is wire 1. Inputs are A and B. Inputs are A and B. Next, second gate and X2. So and X2, output is wire 2. Inputs are A and B. Inputs are A and B. So first I am writing output, then input. Next, third gate is XOR. So XOR X3. Output of this XOR gate is sum. Okay, sum. Inputs are wire 1 and this particular line, if you observe, this particular line is connected to Cin. So it should be Cin. Wire 1 comma Cin. Next, write for AND gate X4. So AND X4. So AND X4, output is wire 3. Output is wire 3. Inputs for this. So inputs for this XOR X1. Inputs for AND gate X4 is wire 1 followed by the same line again here, which is Cin. Wire 1 and Cin. Next, last gate OR gate X5. So OR X5, output is carry. Inputs are wire 3, wire 2. Carry, wire 2, wire 3. And whenever there is a module, there should be end module. I have already explained the execution part of this particular full adder also. Check out my previous videos. So this is the first step in this particular 4-bit adder and subtractor concept. Now this will be our top module. So this is the block diagram which we have seen earlier, where XOR gates are used for the sake of switching. That is, when C input is equal to 0, it should perform addition. When C input is equal to 1, it should perform subtraction. So everything starts with a module. So module name and port list. Port list is nothing but outputs followed by inputs. So output is sum, Cout, A, B, Cin. Next, output 3 down to 0. Here 3 down to 0 indicates size. 3 down to 0 means sum 3, sum 2, sum 1, sum 0, which is vector way of declaration. Next, output Cout. So output is Cout. Next, coming to inputs. Inputs 3 down to 0, A comma B. So 3 down to 0 means A of 3, A of 2, A of 1, A of 0. Similarly, B of 3, B of 2, B of 1, B of 0. Next, input Cin. So this input Cin. Let me check how many wires are there. So C0, C1, C2 are the wires. C0, C1, C2 are the wires. So anything which is present within this dotted box, which is called as a module. And these lines are not having any name, so I am calling it as wires. Next, wire W1, W2, W3 and W4. So here also this particular line has no name. So that's the reason I am giving some name for it, called as wire 4, wire 3, wire 2 and wire 1. Next, coming to gates. XOR some name, XOR N1. So this is first XOR gate. So the instance name for this is N1, N2, N3 and N4. So XOR N1, output is nothing but wire 1, inputs are nothing but B of 0 followed by this Cin. The same thing I have mentioned it here. XOR N1, output is wire 1, input is B of 0 and another input is Cin. Similarly, XOR N2. For this XOR N2, output is nothing but wire 2, inputs are B of 1 followed by Cin, B of 1 followed by Cin. Similarly, XOR N3, output is wire 3, inputs are B of 3, Cin. B of 2, Cin. Next, XOR N4, N4, output is nothing but wire 4, inputs are B of 3, Cin, B of 3, Cin. Next, we have to instantiate full adder. In the previous step, that is step number 1, we have written the Verilog code of full adder. Now we have to call it. So in order to call it, use the same name called as full adder, some name. So the name for this is FA1. Next, outputs followed by inputs. And here remember this point. this format should be same. So first we have to write sum, then carry, then A, B, scene. This is the order in which you have to call it. First sum. So for FA0 output sum is nothing but sum of 0 C0, see sum of 0 C0. Inputs are nothing but A of 0. This input we have to take, which is wire 1 followed by Cin. So A of 0 wire 1 Cin. Next let us try for FA1. So full adder FA1 output is nothing but sum of 1 C1, sum of 1 C1. Inputs are A of 1 wire 2, A of 1 wire 2 and C0. Next full adder FA2 output is sum of 2 C2, A2 wire 3 C1. Next coming to full adder FA3 output is sum of 3 C out, sum of 3 C out. Inputs are A of 3 wire 4, A of 3 wire 4. Input is nothing but C2, and whenever there is a module there should be end module. So just I have described this particular block diagram by means of hardware description language. Outputs followed by inputs is the format that I am using. The last and final step is writing test bench to test it. So module, some name, and here inputs are treated as registers, outputs are treated as wires, and we know that two inputs, that is A is of size 4-bit, 3 down to 0A, 3 down to 0B, Cin. Outputs we are getting 4-bit output sum, that is 3 down to 0 sum, and C out. And this is nothing but instantiation. This is very important. Binary underscore adder underscore subtractor, some instance name followed by output and input. So this name should match with the source code. So let me show you that one. So simply I am making use of this one. So let me highlight it. This one should be there as it is. Simply copy paste this particular line by giving some UUT, means I'm giving some instance name at this particular point. The same line I've copy pasted it here. This one some name followed by outputs comma inputs, and initial begin. Whenever there is begin there should be end. So I'm initializing the value of A to 1010, B to 1010, C input is equal to 0. And after 100 nanoseconds of delay, I am changing the value of A to 4-tick D10 and B as 4-tick D10, meaning that it is again 1010. So D stands for decimal. D is nothing but decimal 10. If I want to write it in terms of binary, it will be 1010. The same thing I have indicated it here, 1010. Here also it will be same thing, but changes C input is equal to 1 here it is 0. So here it should perform addition, here it should perform subtraction, and whenever there is a module there should be end module. And in order to see the result in console window, I am making use of this particular $monitor statement, which will continuously monitor the changes in the values of A, B, C in followed by sum and C out. So whenever there are changes in the values of A, B, C in, the C out and sum we get, that will be continuously monitored, and the result will be displayed in console window. Means it is simply the text format of the waveform. So generally we see waveform, whereas in console window it will be in terms of text format. Once if you synthesize your design, means once if you generate the gate level netlist, you will get this particular RTL schematic, and this is nothing but technology schematic, which is nothing but an elaborated version of it, which contains LUTs, means lookup tables, it contains input buffers, it contains output buffers. This is the waveform for which I am taking values of A as 1010, B as 1010. If C input is equal to 0, I am getting addition operation. If C input is equal to 1, I am getting subtraction operation. So just now I told you waveform followed by console window. So this is waveform and this is nothing but console window. Here you are seeing the result in the form of text format. Instead of waveform, I am getting text format here, so that it will be very easy for us to understand. So this is the overall working and writing the Verilog code of 4-bit binary adder and subtractor. In my upcoming videos, simply I'll copy paste all these codes and I'll execute the same in Xilinx ISE, and let us try to see the result for that execution pattern. Thank you.